Hello, I'm Dominic,
I'm Nathan.
I'm Nick.
And I'm Luke.
and we're Team Make-aroni. And to complete the AEP Make-a-thon challenge, we analyzed the albedo of many surface types to try and maximize solar panel power output.
We used an Arduino kit to build a voltage divider circuit to measure the voltage output from the solar panel. We did this to more accurately read the voltage coming from the solar panel because then we had a known value, specifically the connection to the ground, to compare to.
After we found an ideal resistance, we tested our panel outside during the day with the sun and at night using a flashlight. To do this, we created a rig, as you can see on the left, so that the angle of the solar panel was the same for each trial. We also did some geometry to ensure that we shined the flashlight at the same position and angle every time as seen in the slides. In our code, we collected 3 voltage data points a second for 20 seconds and wrote them to a CSV file.
And here are all the materials that we tested. To analyze our findings, we compiled all the CSV data and found the mean of each solar panel voltage. With that voltage, we calculated the current values using Ohm's law, and then we calculated the power of each material tested. And you can see the data here. The mirror and the aluminum foil recorded the highest voltage, and therefore also measured the highest power output. So you can see in this graph all the different volts, current, and power of each material that we tested. And then in this bar graph, you can also clearly see that the mirror and the aluminum foil have the most power outputted of all of our materials.
Although we completed all these tests with the solar panel fixed to one angle to remain consistent, we did manipulate the angle that the light was coming from when measuring the white cloth. We found that when the angle was decreased or increased from the starting value of 45, the voltage also decreased. When we changed the angle to 30 and 60 degrees, as seen in our diagram, we got voltages of 0.19 and 0.22 respectively, which are less than the 0.317 volts we got at 45 degrees.
So based on our gathered information, we recommend surrounding the solar panels with aluminum material. We know it didn't have the best albedo, but we think it would be more feasible than putting mirrors all over the ground. It also offers a balance between reflecting a fair amount of light while remaining cost-effective. If you wanted a super cost-effective option, you could cover the ground with a light material like white plastic or white cloth.
We also created a device that will help the top side of the solar panel. To help the overall solar panel placement, we use servo motors and wrote a program that will maximize the solar output voltage by moving the solar panel in the direction of the greatest light source. With this design, we were able to increase the volts in another way other than increasing albedo. This solves the problem of the sun moving throughout the day and even throughout the year, as the solar panel can position itself anywhere in its own northern hemisphere. With more time to spend on our project, our team would like to implement a few improvements. First, we would like to run more tests during the daytime and places where the panel could detect lots of natural sunlight.
As stated before, aluminum would be the best material choice. One consideration that could be pursued instead of covering the ground completely is we could direct the light using a dish shape like those used in satellite television below the solar panel, made from the material of aluminum, so that all surrounding light is filtered into the solar panel.
We came in with limited knowledge, even blowing up an LED immediately after receiving our Maker kit. Despite this, Make has been a great learning experience, and we are proud of what we were able to accomplish. We think that the Light Kit Finder has some more applications that we are willing to explore in the future. Thank you.